Hello everyone, welcome to this class. This is Teacher Simon taking you through Cambridge International AS and A-Level Chemistry Paper 2-2 for Feb March 2022. Question 1 is coming from, periodicity. Figure 1.1 shows how fast ionization energies vary across period 2. And we are seeing they are increasing. Okay. Part A, construct an equation to represent the first ionization energy of oxygen, include state symbols. Now, for ionization energies, we look at removal. The first ionization energy, we are looking at removing 1 mole of electrons from 1 mole of a gaseous atom to form 1 mole of 1 plus gaseous ions. Okay, so we have oxygen. It has to be a gaseous atom, and then this one has to lose the electron. Losing an electron, it becomes positively charged. Okay, and then plus an electron. An electron is negatively charged, so it balances this charge, and then we have no overall charge this way, just as on the left. So that is that. Part B, Roman 1, state and explain the general trend in the first ionization energies across period 2. So you can see that the bars keep on increasing. So generally, there is an increase in the ionization energies, but we can see an anomaly here and also here. Okay, so generally it increases. So we shall say the first ionization energies increase across the period. Okay, increase across the period. Why is it like that? This one is due to the increased nuclear charge. Due to the increased nuclear charge. In our explanation, we have to include those factors which affect the ionization energy. Okay, we have the nuclear charge, we have the nuclear attraction. Okay, so the nuclear charge, we are looking at the protons in the nucleus. The more they increase, the number of protons, the more they increase, the more the increase in the nuclear charge. Okay, because protons are in the nucleus and they are positively charged. So the charge on the nucleus gets bigger and bigger every now and then. You add a proton. Okay, then the nuclear attraction for the bonding electrons or for the incoming electrons or the outermost shell electrons. Now here depends on the shielding, because as you keep on adding shells, these shells have gotten electrons, so they keep on repelling. That is the shielding effect. So the more the shielding, or the more you add shells of electrons, then that is how you're going to reduce the nuclear attraction. But nuclear charge has already increased because you are adding the protons. You see that? But then across the period, that is down the group, across the period, you are adding electrons on the same shell. Protons are being added to the nucleus, okay, and electrons are being added to the same shell. So there is similar shielding here, okay. So the attraction, the nuclear attraction for the outermost shell electrons increases. You see that? So we shall therefore have, actually, instead of saying nuclear charge, I will say due to increased nuclear attraction, not charge, okay? I will say nuclear attraction. Nuclear attraction for the valence electrons. For the valency, those are the electrons in the outermost. Valency electrons, okay? For the valence electrons brought by the increase in the proton number. So you are increasing the proton number, then you are increasing the nuclear charge. Then that nuclear charge is the one that is responsible for the nuclear attraction of the valence electrons. Okay, so by the this is brought by the increase in the proton number. Okay, and there is similar shielding. Of the outer electrons. of the outer electrons or valence electrons. So that is all. Then Roman 2, explain why ionization energy A in figure 1.1 does not follow the general trend in the first ionization energies across period 2. So let us look at A here. Yes, I say there is an anomaly here and then here. You expect this one to be higher than this and also this one to be higher than this, but it is not. So why? Now let's look at this element that is here, oxygen. Oxygen has 6 electrons in the outermost shell, right? It is in position 8. So oxygen here is in position 8. Its electron configuration is 1s2, 2s2, then 2p4, okay? So if I, let's say, draw the orbitals, the 2p orbitals, here we are seeing 4 electrons in the 2p. So I first put them as singles and then after I pair, okay? So from here, we can see 2 electrons in this one of the 2p orbitals. That means there is going to be spin pair repulsion. And this spin pair repulsion is going to reduce the attraction, okay? So there are these 2 electrons which are together, okay, in here. They keep on repelling. So in repelling, then this one is far away, okay? As if the radius keeps on increasing. So for that case, the nucleus here is now, the distance between the nucleus and these outermost electrons now increases. So the nuclear attraction now becomes a bit smaller. So therefore, it becomes very easy to remove an electron from. So it becomes very easy to remove an electron from there, and therefore the the ionization energy is going to be smaller. So what we shall say is that the two electrons result into spin pair repulsion. Okay, spin pair repulsion, full stop. This outweighs, okay, this outweighs the increased nuclear charge. Remember, there is an increased nuclear charge. You have added on protons to the nucleus. So there is something this one reduces on the nuclear charge, okay? This outweighs the increased nuclear charge, and therefore it becomes very easy to remove an electron from there. So the ionization energy has to be a bit lower, okay? That is that. Part C, the element E in period 3 of the periodic table is in period 3 of the periodic table. The first 8 ionization energy values of E are shown in here. So we are having that, and they are saying deduce the full electronic configuration of E. Explain your answer. So what is the electronic configuration and then the explanation. Now, we are going to first identify, first of all, if it is period 3, then we must have the principal quantum number here. The last one has to be 3. So we should have 1s2, 2s2, 2p6, okay? This is now 2. Now we go to 3. There has to be 3s, something, maybe 3p. Okay? But now we need to know if at all both of these ones are there. Because period 3, we have sodium, that means here there is 1. We have magnesium, that is 2. If it is aluminium, then we shall have the 1 here, and then the rest like that. So we have that there. Now let's look at these electronic the ionization energies. This is 500, 1018, 1800. Now, this one here becomes 2000. This is 1000, this is 2000, now 11,000. Now, this is 11 to 14. That's a smaller gap. 14 to 18, that is also a smaller margin. Then 18 to 23, 23 to 27. Now I want you to look at from 2 to 11, 2000 to 11. So that is a very big gap. Okay, it's a large jump. So we can see the large jump between the third and the fourth. Between the third and the fourth. So that means that the fourth electron is picked from the inner shell. The fourth electron comes from an inner shell. So this outermost shell has gotten 3 electrons. Okay, so that means if there are 3 electrons, then I will put 2 here and then 1 here. So my explanation is going to be the greatest jump is between the third and fourth ionization energies. So this means that there are 3 electrons in the outermost shell. As simple as that.